Preparing for a Grafana Software Engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a scalable time series ingestion service for Grafana? I would separate ingestion from storage so each layer scales independently. Stateless collectors would validate samples, batch requests, and partition streams by tenant and series hash. A durable queue would absorb bursts, while replicated storage would provide recovery and queryable retention. I would enforce cardinality and payload limits at the edge, expose backpressure instead of silently dropping data, and track ingestion latency, queue depth, rejected samples, and durability. The key trade-off is operational complexity versus predictable performance. While answering, cover ingestion protocols, batching, partitioning, backpressure, replication, cardinality control, durable buffering, tenant isolation, horizontal scaling, and how you would measure latency, throughput, and data loss. Question 2. What are the main causes of high cardinality metrics, and how would you mitigate them? High cardinality usually comes from labels such as user IDs, request IDs, or unrestricted URL paths. I would detect growth through series count dashboards and estimate cost before accepting new labels. At collection time, relabeling or allo lists can remove dangerous dimensions. At application level, I would prefer bounded root templates and logs for individual identifiers. I would also enforce tenant quotas and alert on rapid growth. The goal is preserving diagnostic value without making ingestion and queries unpredictable. Make sure to cover unbounded labels, user IDs, request paths, cardinality estimation, relabeling, aggregation, admission controls, query cost, retention, and communicating safe instrumentation practices to application teams. Question 3. Explain PromQL evaluation and how you would optimize a slow Grafana dashboard query. I first determine whether the panel issues an instant or range query, then inspect its time range, step, and selected series. I use narrow label matchers, aggregate before expensive joins, and choose rate windows that match the scrape interval. For repeated expensive expressions, recording rules are often better than recalculating them interactively. I would also review dashboard refresh frequency, query limits, and caching. Finally, I compare execution time, scanned series, and returned samples before and after each change. In your answer, talk about instant versus range queries, label matchers, rate windows, aggregation order, recording rules, query limits, caching, sampling, and validating improvements with query statistics. Question 4. How would you handle out-of-order samples and duplicate data in a time series backend? I would define the backend's acceptance policy explicitly because retries and distributed collectors naturally create duplicates or reordered samples. A series identifier, timestamp, and value can support idempotent writes when duplicates are identical. For conflicting values, I would reject, choose a deterministic source, or preserve both according to product requirements. I would validate clock skew at ingestion, expose actionable errors, and monitor rejection rates. Strict ordering improves consistency, but bounded tolerance usually gives better availability. Be sure to mention timestamp validation, ingestion ordering, retries, idempotency, deduplication policies, clock skew, replication behavior, error semantics, and the trade-off between strict correctness and availability. Question 5. Describe how you would design a distributed alerting service that avoids duplicate notifications. I would separate rule evaluation, state storage, and notification delivery. Rules could be sharded by tenant and fingerprint, with replicated state recording pending, firing, and resolved transitions. In a highly available deployment, evaluators need coordinated ownership or deterministic deduplication so failover does not send duplicate notifications. Notification attempts would use idempotency keys, exponential backoff, and grouped delivery. Silences and routing belong in the same state model. I would test partitions, restarts, delayed evaluations, and provider failures. While answering, focus on rule evaluation, sharding, alert state, leader election, deduplication keys, notification grouping, retries, ID impotency, silences, HA behavior, and recovery after evaluator failure. Question 6. How would you investigate a memory leak in a Go service used by Grafana? I would first confirm a leak rather than normal heap growth by correlating memory, traffic, garbage collection, and restart history. In a safe environment, I would capture heap and GoRoutine profiles with pprofessor, compare snapshots, and identify growing object types or blocked GoRoutines. Common causes include unbounded caches, forgotten timers, retained request data, and channels that never close. I would reproduce the workload, add a regression test, deploy gradually, and verify stable post-GC memory and allocation rates. Make sure to cover reproducibility, heap and GoRoutine profiles, allocation growth, retained references, pprofessor, load patterns, garbage collection, production safety, regression tests, and verifying the fix over time. Question 7. What concurrency patterns would you use in Go for a high-throughput ingestion pipeline? For ingestion, I would use a bounded pipeline. Decoders feed workers through channels, workers batch validated samples, and writers flush batches to storage. Context cancellation propagates shutdown, while ownership rules minimize shared mutable state. Bounded queues create backpressure instead of allowing memory to grow indefinitely. I would protect unavoidable shared structures with appropriate locks or atomics, run the race detector, and measure queue latency. Graceful shutdown must stop producers, drain accepted work, and close resources in order. In your answer, discuss GoRoutines, bounded channels, worker pools, context cancellation, ownership, synchronization, race detection, backpressure, shutdown ordering, and avoiding unbounded GoRoutine or buffer growth. Question 8. How would you build a reliable plugin system for Grafana data sources? I would define a versioned plugin contract with explicit lifecycle, query, health, and configuration methods. Plugins should be isolated so a crash, resource leak, or malicious request cannot take down the server. Process boundaries are useful for backend code. Capability permissions limit network and file system access, while signing and compatibility checks protect installation and upgrades. The front end needs schema validation and clear error states. I would test protocol evolution, cancellation, slow plugins, and partial upgrades before broad rollout. Be sure to mention plugin contracts, sandboxing, version compatibility, capability restrictions, discovery, configuration validation, front-end and back-end boundaries, signing, upgrades, and failure isolation. Question 9. How would you improve the performance of a Grafana dashboard with many panels? I would start with a waterfall showing query latency, network time, rendering, and panel dependencies. Then I would reduce unnecessary fan-out by combining compatible queries, tightening time ranges, and avoiding repeated variable expansion. Query cancellation should stop work when users change dashboards, while caching helps repeated requests. On the front end, I would virtualize large tables and defer non-critical panels. I would measure time to first visualization, total load time, backend cost, and error rate rather than optimizing one panel in isolation. While answering, cover query fan-out, shared time ranges, request cancellation, panel concurrency, caching, dashboard variables, front-end rendering, transformations, refresh intervals, and measuring time to first visualization. Question 10. Explain how you would implement safe multi-tenant authorization for an observability platform. I would authenticate the user, derive tenant context from trusted server-side claims, and enforce authorization at every resource boundary. Query services must apply tenant restrictions before touching storage, not merely filter results afterward. Cache keys, alert state, logs, and plugin calls must include tenant identity to prevent leakage. Roles should follow least privilege, with auditable changes and explicit service account scopes. I would add negative tests for cross-tenant reads, forged headers, shared caches, and asynchronous job ownership. Make sure to cover authentication, tenant context propagation, resource-level authorization, query isolation, backend enforcement, least privilege, audit logs, cache keys, cross-tenant testing, and defense against confused deputy vulnerabilities. Question 11. How would you design a log search system similar to Loki for efficient querying? I would index a small, bounded set of labels to identify streams, then store log lines in compressed time-based chunks rather than indexing every word. Queries first select streams, use metadata or Bloom filters to skip irrelevant chunks, and scan remaining data in parallel. Limits on time range, bytes, and concurrency protect shared infrastructure. Retention and compaction control storage cost. This design keeps writes inexpensive, but users must accept that arbitrary full-text searches can be slower than heavily indexed systems. In your answer, discuss label indexing, chunk storage, compression, stream identity, time partitioning, Bloom filters, query parallelism, limits, retention, and the trade-off between index size and search flexibility. Question 12. What is distributed tracing, and how would you integrate traces with metrics and logs? Distributed tracing follows a request through services using trace and span context propagated across process boundaries. I would attach trace IDs to structured logs and publish exemplars from latency or error metrics, allowing an engineer to move from an aggregate symptom to a concrete request. Sampling should preserve errors and representative slow paths while controlling cost. I would avoid oversized baggage and treat timestamps carefully because clocks differ. Correlation is valuable only when propagation is consistent and access controls remain intact. Be sure to mention trace and span context, propagation, sampling, exemplars, correlation identifiers, clock limitations, baggage, storage costs, and how links help engineers move from symptoms to root cause. Question 13. How would you evolve a public API without breaking Grafana users or plugins? I prefer additive, backward-compatible changes, new optional fields, stable semantics, and tolerant readers. Before removing behavior, I would publish a deprecation timeline, measure usage, provide migration guidance, and support an overlap period. Versioning is appropriate when semantics genuinely change, but it should not hide inconsistent contracts. Contract tests would run old clients against the new server, while telemetry identifies unsupported patterns. Clear errors and capability negotiation help plugins adapt without guessing which features a server supports. While answering, focus on compatibility contracts, additive changes, versioning, deprecation periods, schema validation, capability negotiation, migration tooling, telemetry, documentation, and testing old clients against new servers. Question 14. How would you debug intermittent query timeouts in a Grafana production environment? I would correlate a failed dashboard request across Grafana, the query frontend, network, and storage using request IDs and traces. Percentiles matter because averages can hide a tail problem. I would inspect fanout width, queue time, connection pools, CPU, memory, disk latency, and upstream throttling. Retries can amplify overload, so I would verify budgets and cancellation propagation. After isolating the bottleneck, I would reproduce with the same query shape, fix the limiting resource, and validate P95, P99, and error rates. In your answer, cover distributed tracing, correlation IDs, latency percentiles, dependency saturation, retries, connection pools, query fanout, timeouts, cancellation, logs, and distinguishing client, network, and storage causes. Question 15. How would you ensure reliable delivery in a Go-based C/CD pipeline? My pipeline would run formatting, static analysis, unit tests, race detection, integration tests, and dependency or vulnerability checks before publishing an immutable artifact. Builds should be reproducible, dependencies pinned, and release artifacts signed. I would deploy progressively behind feature flags or canaries, compare key service level indicators, and retain a fast rollback path. Tests should include realistic storage and plugin interactions, not only mocks. The pipeline is successful when it reduces unsafe change while keeping feedback fast enough for engineers to use. Make sure to cover formatting, linting, unit and integration tests, race detection, dependency scanning, reproducible builds, artifact signing, staged deployment, rollback, feature flags, and production verification. Question 16. How would you test a time series query engine beyond ordinary unit tests? I would combine unit tests with golden query results, property-based generators, fuzzing, and integration tests against realistic data. Important cases include empty ranges, boundary timestamps, staleness, duplicate samples, missing series, label collisions, and large joins. Differential tests can compare optimized execution with a simpler reference implementation. Load tests should measure memory, CPU, latency, and cancellation under concurrency. I would also test malformed queries and resource limits, because robust failure behavior matters as much as correct successful results. Be sure to mention property-based testing, golden outputs, fuzzing, differential testing, boundary timestamps, missing data, label joins, concurrency, resource limits, and validating correctness alongside performance. Question 17. How would you design alert rule versioning and safe configuration rollouts? I would store immutable rule revisions and make activation an explicit operation with validation and audit metadata. A dry run evaluator could show affected series, expected firing changes, and estimated load before rollout. Activation should be atomic per rule group, preserve state where semantics allow, and support immediate rollback to the previous revision. Rate limits and notification grouping help prevent storms. I would monitor evaluation lag and firing deltas after deployment, while clearly identifying who changed what and why. In your answer, discuss immutable revisions, validation, dry runs, ownership, evaluation continuity, rollback, audit history, partial failure handling, tenant isolation, and preventing configuration changes from causing alert storms. Question 18. What observability would you add to an observability product? I would instrument the product around availability, latency, traffic, and errors, then add domain signals such as samples ingested, series created, query bytes scanned, queue depth, alert evaluation lag, and notification success. Metrics should be broken down by tenant, endpoint, and dependency without creating uncontrolled cardinality. Structured logs and traces explain individual failures, while exemplars connect aggregates to examples. I would monitor the monitoring stack separately and define clear runbooks, because observability that cannot be trusted becomes operational noise. While answering, cover golden signals, ingestion and query metrics, tenant-level attribution, structured logs, traces, exemplars, saturation indicators, cardinality, alert quality, and avoiding recursive monitoring blind spots. Question 19. Tell me about an open-source contribution or how you would collaborate on Grafana projects. I approach open-source work by first reproducing the issue and checking existing discussions, documentation, and conventions. I would propose a focused design when behavior or compatibility is affected, then submit a small change with tests and user-facing documentation. During review, I separate technical feedback from personal preference and respond with evidence. If maintainers redirect the solution, I adapt rather than defending sunk effort. Good contributions reduce future maintenance, preserve existing users, and leave the project clearer than I found it. Be sure to mention issue clarification, design discussion, small incremental changes, tests, documentation, review etiquette, maintainer feedback, backward compatibility, and balancing user impact with implementation preferences. Question 20. Design a highly available Grafana deployment for a global enterprise with strict data residency requirements. I would deploy independent regional stacks, placing each tenant's telemetry in an allowed residency region and keeping query traffic local by default. Stateless Grafana frontends can scale horizontally behind regional load balancers, while metadata uses a highly available database with tested backups. Cross-region replication should be limited to permitted metadata or aggregated signals, not restricted raw data. I would define failure domains, recovery objectives, secret management, and capacity thresholds. Regular failover and restore exercises matter more than an untested architecture diagram. In your answer, cover regional isolation, stateless front-end scaling, replicated metadata, tenant placement, data residency, failover boundaries, disaster recovery, consistency, secrets, capacity planning, and operational testing. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.